The overall objective of this lesson is to develop a framework for the description of motion. When I talk about the description of motion, I mean that we will describe the motion of an object quantitatively with the use of mathematical equations. We will describe the motion of an object graphically with the use of graphs, as well as pictorially. That means that we are going to actually draw out how the object moves from one point to another. In simple terms, mechanics is the study of motion. The branch of mechanics that deals with the quantitative description or representation of motion is what we call kinematics. It normally seeks to describe and predict the motion of objects or systems, but doesn't take into consideration the cause and effect of motion. Understand that kinematics provides a mathematical description of motion and does not consider the causes and the effects of motion. That we will study under dynamics. Now, in the course of this lesson, you will hear the word systems quite often. Now, I prefer the use of systems because it really generalizes a lot of concepts and make it easy for you to understand. But what really is a system? Unlike in biology and in chemistry, where the definition of the term system is quite complex, in physics, a system is any object or group of objects we are interested in. For example, if we are interested in the motion of a car, then that car is our system. If we are interested in the motion of a pile of books, then those pile of books represent our system. This means that a system can consist of a single object such as a moving car or a running person, or it can consist of a group of objects such as a pile of books or a car with passengers. Everything in the universe is in motion. From subatomic particles that make up atoms to massive galaxies that contains trillions of stars, they are all in motion. This really makes mechanics the most essential branch of physics that will affect everything that you will study in this course and beyond. Therefore, that explains why we begin, physics with mechanics, because it's the most essential branch in physics. In this course, we will study the motion of things around us, such as moving cars, a ball thrown up in air, an athlete competing in a race. So even though we will avoid complicated motions such as the zipping of galaxies through space at very high speeds, the spin of electrons within an atom, the analysis of the motion of everyday objects can still be very complicated. Let me give you some examples so that you should agree with me that the motion can be very complicated. Take, for example, a ball thrown up in air. The motion of a ball thrown up in air is affected by the downward gravitational pull of the earth. That's why it falls back in the first place. It's affected by wind, by air drag, humidity, the elevation, and the buoyant force. In addition to all of these factors, the ball spins about its center of mass as it moves through air. So if we take into consideration all these factors, the mathematics involves in solving or analyzing the motion of a ball thrown in air will become very complicated and certainly will be beyond the scope of this course. Now think about for a moment, have you ever watched a bat thrown in air? Its motion is even more complex than the ball. Certainly you agree with me that a simple motion of an object as simple as a ball thrown up in air really is very complicated if we take into consideration all the factors that affects the motion of such a ball. Let me give you another example. Have you ever observed yourself or someone walk or run? If not, why don't you try that right now? You will notice that as you walk, you move your right and your left leg alternatively back and forth while simultaneously swinging your arms backwards or forward. This process gradually moves your body forward or backward. Think of all the moving parts, the legs, the arms, the oscillating head up and down. If you take into account all of these moving parts, it will certainly make the analysis of motion as simple as walking exponentially very difficult. Visualize a moving car along a road for a moment. What could possibly affect the motion of a moving car? Think for a minute. The road is rough. There's friction between the tires on the road. If you place your hand outside of a moving car, you can certainly feel the wind bashing through your palms. As we have air resistance and drag forces, well, that is a simple experiment to show that wind and air resistance also affect the motion of cars. It could be rainy, it could be snowing. All of these factors really affect how a car moves. So this brings me to one essential question. How do we uncomplicate or simplify complicated motion? If the motion of everything in our life really is that complicated, so how do we study such complicated objects? You see, in this course and in physics in general, we introduce the concept of models. This is very important. Now, you may not find this in most traditional textbooks, but the concept of models is really essential for your understanding of physics. So the question is, what is a model? Different authors define the word model differently. And really, I do not want to get into the fight of which definition is the most correct definition. Each of those is probably correct within its own context, but in this course, and generally in physics, a model is a simplified theoretical representation or description of a physical system. Let me say that again. A model is a very simplified representation of a physical system. Now, a model can also be a physical equation that can be used to predict the behavior or how a system will move under a given set of assumptions. Therefore, we can also define a model as a simplified abstract representation of a real-world phenomena. Now, what does this have to do with what we are doing? The reason I am introducing modeling or models is because the study of objects in nature really is complicated. To make things easy on you, we will introduce a simplified representation of the motion of a system such as a car or a ball by making certain basic assumptions. For example, we may assume that there is no friction, there is no drag, there is no air resistance, to make the motion of a car simple to analyze mathematically. When we make those assumptions, what we are dealing with is a simplified version of what actually is. That is a model. Understand that a physical model is correct if it can accurately predict the position of a system as a function of time, provided all its fundamental assumptions are made. Let me say that again. If all the fundamental assumptions of a given model are met, if that model can predict accurately the behavior or the position of a system with time, then that model is said to be correct. Now, in this context, a system really is an object such as a car or a group of objects such as a set of books whose motion we are interested in. So anything that we are obviously interested in physics or at that particular time, we call that thing a system. Now, the importance of developing models is that it will help you to compartmentalize a broad array of core concepts in physics. And when that happens, you can easily relate one core concept to another. It may not seem obvious to you, but this particular approach provides a systematic framework on how to tackle physics problems and make sense of the solutions that it produces. It is important to note that when a physical equation is used to model the behavior of a system, there is always a physical law that governs that particular model. Now I'm going to give you examples of different models and I will show you how it works. One of the first models that we will talk about is the particle model. Now, the particle model is an example of a physical model. In this model, all objects are considered to be point-like in nature. Now, before we discuss this model any further, I would like for you to watch this demonstration from the Department of Physics at MIT. You see, in this demonstration, just observe the center of mass of the object as it is being tossed around. Now, the first video will demonstrate the object being tossed around with the center of mass painted. Looking at the system as a whole, the motion will look very complicated. But when you observe just the center of mass without looking at the system, you will see that the motion becomes very simple. So the whole point is, what this demonstrates is that by considering only the motion of the center of mass, we can treat the system as if all its mass were concentrated into this single point. Now, an object whose size and dimensions are irrelevant in describing its motion is what we call a particle. Let me say that again. A particle is an object whose size and dimension is irrelevant in the description of its motion. That means that if we model a system as a particle, we can represent that system as a simple dot rather than having to draw the full picture of that system. Now, the motion of a particle system can only be linear or oblique. Let me say that again. The motion of a particle system can only be linear, which is one-dimensional motion along a straight line, or it can be oblique, which is a two-dimensional motion, such as a projectile motion. When we say that the motion of an object is one-dimensional, it can only be forward or backwards. That means that we can indicate the forward direction to be positive and the backward direction to be negative. Two-dimensional motion can be both forward or backward or upwards or downwards, which means that an object can be projected obliquely at a certain angle. We will study this under projectile motion. Now, the particle model removes any spinning effect or rotation, which means that when we approximate a system as a particle, that system can only undergo linear motion or oblique motion. So this brings us to a very important question. How do we describe the motion of a system? How do we describe the motion of a system? Now, to describe the motion of an object or a system, we need to keep track of the object's position at different instants of time. Let me say that again. To describe an object's motion, we need to keep track of the object's position at different instants of time. Now, an object or a system is said to be in motion if its position changes with time. In other words, if the position of a system changes as time passes, we say that the system is moving. But if the position of the object or system is not changing, we say that the system or object is at rest. Therefore, we can define motion as a change in the position of an object with respect to a given frame of reference. Let me say that again. Motion can be defined as a change in the position of an object with respect to a given frame of reference. So the question is, what is a frame of reference? That is a new term that I have just introduced. Now, the best way for me to explain what a reference frame means is, just imagine that you are observing somebody pass by. You are the observer observing the person running towards you or maybe away from you. Now, a frame of reference, you, the observer, plus a clock and a coordinate axis constitute what we call a frame of reference. The clock enables you to measure time. The coordinate axis enables you to measure position. But the unique thing about any frame of reference is that the observer must be fixed relative to that particular frame of reference. In other words, to measure motion, two things are important: the observer who is doing the measuring and the object of interest, our system that is moving. Now, a coordinate system plus a clock plus our observer constitute what we call a frame of reference. Remember, the coordinate system helps us to measure the position of the object of interest at different instances of time. Now, let us analyze the motion of a man jogging.